All right, so it looks like you're gearing up for a senior software engineer interview, and you're really diving deep into graph databases. That's fantastic. It shows you're serious about this, and it looks like you've got a whole stack of resources here. We're going to help you make sense of all of it. So instead of just skimming the surface, we're going to help you really understand the core concepts of graph data models. That way you can walk into that interview feeling confident and ready to answer even the toughest questions. Now, I'm super excited to explore this topic with you because you always have such a knack for taking these intricate topics and breaking them down in a way that just clicks.
Well, thank you. I appreciate that. I think a great place to start would be by comparing graph databases to something that I'm sure you're already very familiar with as a senior engineer, and that is relational databases.
Yeah, that makes perfect sense. I mean, as senior engineers, we've all spent countless hours working with relational databases, tables, rows, all that good stuff. But where do graph databases come in? When are they actually a better choice?
That's a great question. Relational databases, they work really well for structured data, but when you start dealing with data that's highly interconnected with lots of complex relationships, that's when they start to struggle. Think of a social network like Facebook. You've got users, friends, posts, comments, likes. It's this massive web of interconnected data. Trying to represent that in a relational database using tables would be a nightmare.
Yeah, I can imagine all the joins and foreign keys you need to make that work. It could get really messy really fast.
Yeah.
So how does a company like Facebook, with all of its data, actually handle this in the real world?
They use a graph database. In fact, they use a single giant graph to store practically all of their data, and that's a key takeaway here. Graph databases excel at representing these complex, interconnected relationships in a way that relational databases just can't match.
That's incredible. It really speaks to the power of this approach.
Yeah.
So I'm curious, instead of using tables and rows like we do in relational databases, how do graph databases actually model these relationships?
So let's talk about a very common type of graph database called property graphs. They have a pretty simple but really powerful structure. You have vertices, also known as nodes, which represent entities, and then you have edges, which represent the relationships between those entities.
Okay, so I'm picturing nodes as dots and edges as the lines connecting them, like a visual representation of a network.
Exactly. And what makes property graphs so powerful is that both the vertices and the edges can have properties. These properties are essentially key value pairs that store additional information about the entities and the relationships. So for example, if you had a node representing a person, you could have properties for their name, their age, their location, anything you want.
Ah, that makes sense. It's kind of like object-oriented programming, but for data. Nodes and edges with properties, just like objects have attributes.
Exactly. It's a great way to think about it. And just like in object-oriented programming, you can use these properties to define the characteristics of your data and to model real-world relationships in a very flexible way. Let's go back to that Facebook example for a second. Each user would be a node, and the friendships between users would be represented by edges connecting those user nodes. You could even have properties on those edges to store information about the friendship, like when it started or maybe common interests they share.
Wow, that's such a clear way to visualize it. I can really see how this approach would make it so much easier to understand and analyze those complex relationships in a social network.
Absolutely. And that brings us to another important concept, querying the graph. Once you have your data modeled as a graph, how do you actually extract meaningful information from it?
That's a great question. I'm guessing SQL isn't really the right tool for this.
You're right. SQL isn't ideal for querying graph data. Luckily, there are specialized graph query languages that are much better suited for navigating relationships and extracting insights from graphs. One of the most popular languages is called Cypher.
Cypher. Okay, I've heard that name before. Can you give me a basic sense of how it works without getting too deep into the technical details?
Sure. The main idea behind Cypher is to express your queries in terms of patterns in the graph. So instead of thinking about rows and columns, you're thinking about nodes, edges, and the paths that connect them. For example, let's say you wanted to find all the friends of a particular user on Facebook. In Cypher, you'd write a query that essentially says, start at this user node and follow all the friend edges outward to find the connected nodes.
So it's like tracing paths through the graph, following the relationships to find the information you need.
Exactly. And that's what makes Cypher so powerful for working with graph data. It lets you express these really complex relationship queries in a very intuitive and readable way.
This is starting to make a lot of sense to me. I can definitely see how understanding a language like Cypher would be a valuable skill for a senior engineer. especially when you're dealing with graph data.
Absolutely. It shows that you have a deeper understanding of data modeling and the ability to work with different types of databases. Now, I know we've only scratched the surface of graph databases, but I think this gives you a solid foundation to build on.
Yeah, I feel like I've got a much better grasp of the basics now. But I'm curious, are there other types of graph databases besides property graphs? I'm looking at my notes and I see something about triple stores.
You're right. Triple stores are another popular type of graph database, and they're conceptually similar to property graphs, but they use a slightly different terminology.
Okay, I'm all ears. Let's dive into the world of triple stores.
Triple stores are built around this idea of representing data as triples. Subject, predicate, object. It's like a simple sentence that describes a relationship.
So instead of nodes and edges, we have subjects, predicates, and objects. Can you give me like a real-world example? Just help me wrap my head around this.
Sure. Let's say we want to represent the fact that Marie Curie won the Nobel Prize in physics. In a triple store, Marie Curie would be the subject, won the Nobel Prize in would be the predicate, and physics would be the object.
Okay, I see how that forms a statement about the relationship. But how does this relate back to property graphs? Are they doing something fundamentally different, or is it just a different way of looking at the same thing?
It's more like a different dialect of the same language. Conceptually, they're very similar. In a property graph, you'd have a node for Marie Curie, a node for the Nobel Prize in physics, and an edge representing the one relationship between them. Triple stores just use a different way of expressing that same information.
So the underlying concept is the same, but the syntax, the terminology is a bit different.
Exactly. And just like property graphs, triple stores have their own query languages that are designed to extract information from the graph. One of the most common languages for triple stores is called SPARQL or
SPARQL. Okay. Now, I remember from my reading that SPARQL is also based on pattern matching similar to Cypher. Would it be fair to say that these languages are more alike than they are different?
yes and no. They both rely on pattern matching to traverse those relationships and find the information you're looking for. But there are some subtle differences in their expressiveness and the types of queries that they're really good at. For example, SPARQL is very well suited for querying data that's super interconnected and involves complex reasoning about relationships.
Interesting. So if I were designing a system where I needed to make inferences about relationships, SPARQL might be a better choice.
It could be yes, but the choice of language really depends on your specific needs and the type of data you're working with. I think the main takeaway here is that there are multiple powerful tools out there for querying graph data, each with its own strengths and weaknesses.
That's really helpful to know. I feel like understanding these nuances of these different languages and when to use which one could be a real differentiator in a senior engineer interview.
Absolutely. It shows you can think critically about data modeling and you know how to choose the right tool for the job. Now, before we move on, I want to address something that often comes up when people are learning about graph databases. How do they actually store the data?
Oh, that's a great question. I've been kind of wondering about that myself. I mean, we keep talking about nodes and edges, but how does that actually translate into a physical storage mechanism?
You might be surprised to learn that you can actually represent graph data using a relational database schema.
Wait, really? I thought we just talked about how relational databases aren't ideal for handling complex relationships.
They're not ideal for querying those relationships, no, but they can definitely be used for storage. Think of it this way. You could have one table for vertices where each row represents a node, and another table for edges where each row represents a connection between two nodes.
Okay, I'm starting to see how that would work. The edge table would essentially define the relationships by referencing the IDs of the starting and ending nodes.
Exactly. And you can even include additional columns in that edge table to store properties associated with the relationship. So even though we're using relational tables, we're still capturing the essence of a graph.
That's really interesting. It kind of highlights that the power of graph databases isn't just about the storage, but about having the right tools to query and traverse those relationships efficiently.
Precisely. It's not just about storing the data, it's about having the tools to navigate and analyze those relationships effectively. Speaking of navigating relationships, let's shift gears for a second and talk about how graph databases handle different levels of granularity in data.
Okay, I'm intrigued. What do you mean by granularity in this context?
Well, think about real-world data. It often exists at different levels of detail. For example, in that family tree example we were discussing earlier, you have individuals, families, cities, countries. Sometimes you need to work with very specific information like a street address, and sometimes you need a more general view like just a region or a country.
Right. I can see how that could be a challenge to model effectively. How do graph databases handle that kind of hierarchical data?
Beautifully. You can have vertices representing different types of entities at various levels of detail and edges defining the relationships between them. For instance, you could have a node for London, which is connected to a node for England, which in turn is connected to a node for United Kingdom. And then you could have someone's lives in edge pointing directly to the London node.
Ah, so you're essentially building a multi-level map of the data where you can zoom in and out to see different levels of detail.
Exactly. And that's something that would be pretty tricky to model cleanly in a traditional relational database. With graph databases, you have that flexibility to represent those hierarchical relationships in a very natural and intuitive way.
That makes a lot of sense. Seems like graph databases are all about embracing the complexity of real-world relationships rather than trying to force them into this rigid tabular structure.
You got it. And that flexibility is a big reason why graph databases are becoming so popular for applications that involve complex, interconnected data.
This is all super helpful. I feel like I'm starting to develop a much deeper understanding of how graph databases work and the problems they're designed to solve.
That's great to hear. But remember, we've only scratched the surface here. There's a whole world of fascinating concepts and techniques within graph databases.
I'm ready to keep exploring. What other insights can you share that might help me really stand out in that senior engineer interview?
Well, let's talk about some real-world applications of graph databases. Understanding where and how they're being used can give you a better appreciation for their power and versatility.
Okay, let's do it. I'm eager to see how these concepts are being applied in real-world scenarios. So we've talked about all this theory behind graph databases, but I'm curious, what are some practical examples of how they're actually being used out there in the real world?
Well, one area where graph databases are really making a huge impact is fraud detection. So imagine you're a financial institution and you're trying to identify patterns of suspicious transactions.
Okay, I can see that. I'm picturing a whole network of accounts and transactions. How would a graph database help uncover something fishy going on?
Well, with a graph database, you can easily analyze all the connections between those accounts. You can look for unusual patterns. For example, you might find a group of accounts that were all open around the same time with similar fake identities, and they're all funneling money to a central account. That's a classic sign of fraud.
Right, it's like connecting the dots. Instead of just looking at individual transactions, you're looking at the big picture and seeing how everything is related.
Exactly. And that's what makes graph databases so powerful for fraud detection. They allow you to see those hidden connections that would be very difficult to spot with traditional methods. Another really cool application is recommendation engines.
Oh yeah, like what Netflix or Amazon use to suggest movies or products you might like.
Exactly. Think about how those recommendations work. They analyze your past behavior, what you've watched, what you've bought, and then they use that information to find other users with similar tastes. And then they recommend items that those similar users have enjoyed.
So it's all about finding those patterns of relationships between users and items.
Exactly. And graph databases are perfect for this because they allow you to model those relationships in a very natural and intuitive way. You can have nodes representing users and items and edges representing actions like watched or bought. And then you can use graph algorithms to traverse those relationships and come up with those recommendations.
Wow, this is fascinating. It seems like graph databases are giving us a whole new way to understand and leverage the power of connections.
They really are. And that's why they're becoming so important in all sorts of fields like social network analysis, knowledge management, and even drug discovery. But let me ask you this. Do you think there are any situations where a graph database might not be the best choice?
That's a great question. Now that I think about it, if your data is very structured and tabular and you don't really need to analyze relationships, a relational database might be a simpler and more efficient solution.
I agree. If you're mainly doing simple lookups and updates and you don't have a ton of complex relationships, a relational database is probably a better fit. And of course, performance is always a consideration. Graph databases are optimized for relationship queries, but they might not be the fastest option for certain types of analytical queries.
Look, it's all about choosing the right tool for the job. There's no one-size-fits-all in the world of databases.
Exactly. And sometimes the best approach is to use a combination of different database technologies. You could use a relational database for your core transactional data and a graph database to model and query specific relationships within that data.
Ah, so a hybrid approach. That's interesting.
The key is to understand the strengths and weaknesses of each technology and design a system that meets your specific needs. And for a senior engineer position, that's the kind of insight that can really set you apart.
This has been such an eye-opening deep dive. I feel like I've gone from zero to hero on graph databases. I'm actually excited to talk about this stuff in my interview now.
That's great to hear. And remember, even if you don't have all the answers, the most important thing is to show your curiosity, your willingness to learn, and your ability to think critically about complex technical topics. And if you can showcase your understanding of graph databases and why they're so valuable, you'll definitely make a strong impression.
This has been so valuable. I feel so much more prepared and confident going into this interview. Thank you so much for taking the time to share your knowledge and expertise.
My pleasure. Good luck with the interview.
Thanks again. And to all our listeners out there, keep diving deeping, keep exploring, and never stop learning. Until next time, this is The Deep Dive signing off.